Hello, hi everyone. Am I audible? Hello everyone. Can you all hear me? Just let me know. Okay, some people are here. That's nice. So, hi everyone. My name is Pradyumn, and today we will solve the problems from A to E of today's CF round, which was Div 2. And I am Pradyumn. So, but before moving on, I'll tell you about our courses at TLE Eliminators. So, if you are someone who wants to level up in CP and you are stuck at just solving one or two problems per contest, then these courses are exactly what you need. They are self-paced courses, and we have structured the program into four levels so that you can start from wherever you are: beginner, pre-intermediate, intermediate, advanced, and you will learn the most relevant CP concepts through video lectures combined with guided hints for practice problems and also the video solutions. And they help you understand the why and not just the how to give actual intuition, right? And if you need more help, you will get instant doubt support from our higher rated mentors, so that you're never left stuck. And if you need more help, um, you can contact them on Discord, and instantly you will get resolved, right? And beyond just learning, you can enjoy leaderboards, progress tracking, internal contests, and PCDs like this one to keep you consistent. So you can pick the level that fits your goals and start learning today. If you're not sure that which level you should choose, then you can watch this video, which tells you how to choose a level, right? And if you're still not sure, then you can watch the level specific video, which tells you about that. So it details the prerequisites, outcome, difficulty, and topics. All right. So let's move on to the PC now. Okay. So this was today's contest, and I solved five problems from A to E. Somehow this F has more solves than E, but I did not solve it, and I am pretty sure that they are AI solves. Most of them are AI solves. But anyways, so problem A. A is given an array A1, A2 up to AN. In one operation, you can choose a pair of indices I, comma j, such that I is less than j and AI is greater than aj, and remove the element at index j. After that, the size of the array will decrease by 1, and the relative order of the elements will not change. Find the maximum number of operations that have been performed on the array if they are applied optimally. Okay, so the problem is that what you have is you have an array A1, A2, A3 up to AN, right? And what you can do is you can select any two indices I and j such that I is less than j and AI is greater than aj. That is, you can select any two numbers such that the bigger one appears first and smaller one appears later, right? And then you can delete the smaller one. Okay. So for example, you have 514 31452 as your array, 31452. Then you can delete this 5 and you can delete this 5 because you can select 3 and 5. So sorry, my bad. You can delete this 2 because you can select this 3 and 2. So the bigger ones come first and the smaller one comes later. So you can delete the smaller one, right? So you can delete this 2. Also you can delete um, this 1, right? So if you do this, then you will be left with, like, you will have deleted two numbers, right? And this is optimal. So 2 is the answer. Like, they are asking that if you can do this operation, then what is the maximum number of times, maximum number of times that you can do this operation, right? So yeah, that's the problem that we have been given this a1, a2 up to an, right? Now guys, just tell me that if I want to delete some element I, okay, or let's say j, like let's say I have some element ai here, or okay, I just have an index j and I have this array, right? And I ask you that I want to delete the element aj. I want to delete this. So when can I do that? When can I delete aj? So the condition for that is that there has to be some element which is greater than aj, which is behind aj, right? There has to be some element in the index 1 to j minus 1 such that that element ai is greater than aj, right? So like if you had to choose an element, like if you could check only one element from this, you would take the maximum element, right? Like see what I'm saying is, let's say you have 3 1 4 5 2, and let's say you have 3 as well. And I say to you that check, like, can you delete this 2 or not? Can you delete this 2 or not? So you want an ai which is before this 2 and which is greater than this 2, right? So what you will do is you will check the maximum element before this 2, right? Because that has the highest chances of being greater than 2. If the highest one, if the maximum element is also less than equal to 2, then of course all of them are less than equal to 2, right? So what you can do is just check the maximum value and see if it is greater than 2 or not. So since it is greater than 2, you can delete this 2, right? So that's how you can see that can you delete an element or not. So basically some elements are not deletable. Like let's say if you take this 5, if you take this 5, then definitely you can't delete it. Why? Because there is no element which is greater than 5 before here, right? But um, so basically we know that which elements we can delete, right? So I can delete this 1 because this 3 is greater than this 1. I can delete this 2 because 5 is greater than 2. And I can delete this 3 because 5 is greater than 3. So I can delete these 3 elements, but can I delete them simultaneously? Like I know that from this array I can delete this 2. From this array I can delete 1. From this array I can delete 3. But can I delete all 3 of them? So the answer is actually yes. Why? Because you can simply delete them from left to right. Like just delete these elements from left to right. Like let's say if you delete this one, okay. So the fact that you deleted this tells us that there is some element which is more than that, right? Like the fact that you deleted this one tells us that it is not the maximum in this range. So 1 is not the maximum, right? So deleting 1 will not affect the condition of 2, right? Like we said that this 2 is deletable because the maximum in this prefix was greater than 2, right? So even if I delete this 1, this maximum will not change because 1 was not the maximum. So I can just simply delete this, then I can simply delete this one, and I can delete this one as well, right? So the answer would be 3. So just count the number of numbers which are not the prefix maximum, right? That's the actual idea. That basically you can count the number of indices j such that the maximum from 1 to j minus 1 is greater than aj. That is the only thing. So you can simply iterate from left to right in the array. Go from left to right and just keep a maximum, a prefix maximum. Like just keep a max p max element and it will store that what is the maximum until this point. Let's say if you are here, then maximum until this point it will store, and just compare it with A3 and update it after comparing it with A3, right? So this is how you can implement this problem in O of n. Okay, so I think it should be clear. Yes, I solved E also. Like I solved it at 159 at the last moment. Okay, so A and B, sorry, problem A, is it clear, guys? Any doubts? Thanks, man. Okay, let's look at the code, and meanwhile you can ask any doubts if you have. Okay, so the code is just this simple. Int n, c in n, then take the input of the array A. So like int arr n, and for int I equal to 0, I less than I plus plus, c in ai. Okay, and I am having this ma variable which is the maximum index. I mean the maximum value until the prefix. So of course the first element can't be deleted, right? By definition, you cannot delete the first element. So I start from I equals to 1. So the maximum is initialized to a of 0. Okay. So for I equal to 1, I less than I plus plus. If ai is less than ma, that is, we can delete this ai. So ans plus plus. Otherwise, ma equal to ai. So I update the maximum. Like if ai is greater than equal to the maximum, then I set the maximum equal to a of I, right? And then just print the answer. Okay. So I'll count till, I will wait till 12:50 in this timer, and you can ask any doubts if you have. Okay, I think there are no doubts, so I'll move on to the next one. So B was optimal shifts. You are given a binary string S1 S2 up to Sn containing at least one 1. You want to obtain a binary string of the same length consisting of all ones. To do this, you can perform the operation any number of times. Choose a number D and consider string T as cyclic right shift of the string S by D, or more formally, T equals to this S of n minus D plus 1 up to Sn and S1 to Sn minus D. After all that, for all j, after that, for all j, for which Tj equal to 1, perform Sj becomes 1. The addition operation costs D coins, where D is a chosen shift amount, right? Note that the positions Note that the positions in the string S, where initially Sj equals to 1, remain equal to 1, even if Tj equal to 0. So basically you are taking an OR. String S becomes S or T, right? You need to determine the minimum number of coins that can be spent so that the string S consists only of ones after all the operations. Okay. Yes, that is correct, I guess. Rating has come. Let's see. Cool, cool. Plus 38. Anyways, so optimal shifts. Yeah. So the problem says that we have initially a string S, right? And it is a binary string, like only zeros and ones. So 0 0 0 1 0 1 1 0, something like that. Okay. And basically what we can do is we can um, take a string t, which is a shift of s by d steps, right shift, right? So let's say if I take d equal to 3, okay. So if I right shift this 3 times, then t becomes 110, then 00010, right? So if I do the operation with d equal to 3, then my t is this, and I can assign s goes to s or t. So like at every position where t is 1, I can have 1 in s, right? So if I take the or, here I'm writing is t, right? So if I take the or, it becomes 1101 0 1 1 0, right? This string s becomes, so after doing the operation with d equal to 3, s becomes this, right? And the cost of this is d, okay? And you can do it as many number of times as you like, but finally the string s must be all ones. We have to make s as 1111, right? So what is the minimum cost of achieving this, right? So how would we solve this? Now, the main idea here is to see the samples. So like just see the samples. Let's say you have, okay, it is not very, it is very long. So I will make it a little bit shorter. Like let's say you have this string 100 0 1 0. Okay. So essentially what you want to do is you want to like you want to make all of these zeros to ones. Like these two are already one, right? But you want to make the zeros which are there in the string s to 1, correct? So how would you do that? You have only one way, right? You can shift this string and then you can perform the or operation, and it will cost the number of times that you shifted d, right? So just think about this, that let's say if you want to convert this 0 to a 1, okay, then you'll need a 1 at that point, right? Like whenever you are taking a bitwise or with t, you would need a 1 here in t, right? Then only this can become 1 in the new string s, correct? But after, like if you want a 1 here, that means that let's say if you want in the next turn only, if you want a 1 here, then you will have to shift 3 times, right? So like if you shift this right 3 times, then it becomes 0 1 0 1 0 0, right? So you shifted right 3 times, and then only a 1 came here. So it costed you 3 operations just to make this 1, right? So can you do better? Like it is allowed that you can break it into multiple operations, right? So can you change this 0 to a 1 in less than 3 cost? Can you do that? My question is that can you change this 0 to a 1 in less than a cost of 3? So my claim is that no, you can't do that, because you have to move this 1 like this, right? Like the closest thing to the left is this 1, right? So you have to transport it here. So either you can like maybe do an operation with 2, like first do d equals to 2. So this one would come here. That is this bit would become 1. Like if I do this 1 0 1 0 0 0. So as you can see that this bit became 1. So basically you wanted to make, okay, you wanted to make this 1 1, and the closest thing that is there is this. So you're trying to transport it here, or actually here. Sorry, what I'm saying, I am saying that you want to make this bit as 1, right? And the closest one to the left is this one. So you'll have to move this to here somehow. So if you did in one operation, then it will cost us three coins, right? But even if you do it in more than one operation, then also it will cost at least three. Like if you, let's say, transport this one onto here first, right? So here there's a one now, and now you transport it here. So like you shift one to the right, but that is again costing you 2 plus 1, which is 3 coins, right? So my claim is that no matter what you do, doesn't matter what you do, you will always incur a cost of 3. Like if you want to make this 0 to a 1, then you will always have a cost of at least 3. Okay, so for just this one bit the cost is 3. So of course our final answer is also at least 3, right? Basically we cannot make this bit as 1 in less than 3. So of course we cannot make all of them as 1 in less than 3. And like why 3? 3 is just the closest one to the left. Like to the left of this, what is the closest one, right? So for all the zeros, you can calculate that. Like for this zero, the closest one is at distance of 1 away, right? Then for this 0, it is at 2 distance away. Then for this 0, it is at 3 distance away. Then this is a 1, so we don't care. And for this 0, the closest one to the left is at a distance of 1, right? Sorry. So our answer is at least 3. Like our final answer is at least 3. That's what we know. But can we do it in 3? That's the question. Like, is the answer actually equal to 3? We have to figure out that can we do it in 3 operations or not. So can we figure out a way to do it in 3 operations? So yes, it is very trivial. You can simply do the operation for d equal to 1 3 times. Okay, like just shift this once. So these two would become 1, right? Then again shift this. So like this would become 1, and then again you can shift this. So these two would become 1, right? So you can simply do an operation of d equal to 1 3 times, and you can be sure that every 0 is going to become a 1. Like why do I say that? Let's say you have a 0 right here and a 1 here at a distance of x. Okay, so like after you do x moves with d equal to 1, then essentially this one has shifted x times to the right. So this one has now reached here, right? So this has become 1, right? So for every zero, you are checking its maximum. Like here in this string, you figured out that uh, their value was like basically 1 0 0 0 1 0, right? So you found out 1 2 3 and 1. So you took the maximum value, right? So as soon as you shift by 1, these two will get these two ones, like those two zeros which have 1 as their value will transform to 1. Then when you do it once more time, like when you do it once more, this 2 will get converted, and then you do it once more, this 3 will get converted. So the entire string would be 1 1 1 1, right? So basically I proved that the answer has to be at least 3 for this string. For this string, I proved that the answer has to be at least 3 because I want to make this 0 to 1, and then I showed you how to do it in 3 operations. Like it is possible to do it in 3 operations. So the answer is actually 3. And in general the answer is basically um, whatever is the maximum distance of a 0 from the 1, like to the left of it. Okay, like this 0 is here, and the closest one is at a distance of 3. So you'll find out the distance closest to every 0 and take the maximum. Okay, and that's the answer. And actually, if there are some zeros before the one, like if there, let's say a string is like this, so there are no ones. Like if you look at this 0, there are no ones to the left of it, but it is cyclic, right? So you can go back like this, and this is the one which is to the left of this 0, and its distance is what, 1, 2, and 3. Okay, so for this 0 the value is 3, for this one it is 2, for this it is 1, and for this 0 the value is 1 because of this 1, right? So the answer for this string is also 3. Okay, and like this is the answer is the maximum of values of all zeros, right? Where value means the minimum distance of a 1 to its left. And actually some people are also saying that the longest run of zeros, like in this given string, how many number of times zeros occur in a line, like continuously, whatever is the maximum of that. Like let's say if I have a string, okay, so here 0 comes 3 times, here 2 times, here 1 time, here 2 times. So 3 is the answer, right? And the same thing it is. Why? Because the value of this last 0 in that longest block is 3, right? So it is the same thing, right? I coded it like this: answer is equal to maximum of values of all zeros, but this is also fine, that it is the maximum run of zeros, but after accounting for the cyclic thing, right? Like for this string, the answer is 4, because the string is cyclic, right? So these 4 zeros, they are of same group. Okay, and using my formula, the value for this 0 is 1, for this one it is 2, for this one it is 3, and for this one it is 4. So that's why 4 is the answer, right? So that's how you can solve this. Yeah, I think it is pretty clear to everyone. Any doubts, if there are, you can ask. Okay, that's nice. Okay, I will show the code of B and then I'll move to C. I will discuss till E. Raghav. Okay, so sorry, int and cns, string as cns, and what I'm doing is first finding out the last occurrence of one. Okay, like what is the position at which one appears rightmost, right? So this last variable contains that. Okay, then I just find out the value for all zeros. Okay, so like what I'm doing is I'm iterating from left to right. Let's say in this string, basically I have a variable which keep tracks of what is the closest one. Okay, so currently that variable is -1. When I'm here, it is -1. It is -1. Then when I reach here, the variable becomes 2. That is the index. So index is like 0, 1, 2, 3, 4, 5, 6, 7, right? So it becomes 2. Then I move here. So I'll do 3 minus 2. Like the value for this 0 is 3 minus this 2. Then I move here to this 4. So the value for this 0 is 4 minus 2, which is 2. Then I move here, it is a 1. So I change this variable to a 5. Right? So for this one, it is 6 minus 5, which is 1. And for this one, it is 7 minus 5, which is 2. But for these two, how do I find the values? I have to know the index of the last one, right? Like when I'm going back cyclically, I have to know the value of the last one or the index of the last one, right? So for that, I know it is 5, right? I just calculated it is 5. So what I'll do is 0 plus 7 minus 5 or 8, sorry, 8 minus 5. Basically, if I'm at index I, so I plus n minus last. That is the formula, right? So here 0 plus 8 minus 5, which is 3, and 1 plus 8 minus 5, it is 4, right? So that's what 4 is the answer. So initially, I initialize this variable, which is to minus 1. It is this variable, that what is the latest one that we have seen. So initially it is minus 1 because we haven't seen any ones, right? And so while it is minus 1, I will keep using this last variable. I'll cyclically keep going back. Okay. So there to I iterate over the string, and if s of I equals to 0, then if first is minus 1, then I'll cyclically go back. So I plus n minus last. Otherwise, I minus first, right? So this is for si equal to 0. And if si is 1, then I'll update my first variable. And so I will take the maximum of all these values in my ans variable. And I'll print the ans variable finally. Okay. So I hope it makes sense. Okay. Shit. Sorry. Yeah, so this was B. C is called old process. You have n coins with denomination A1, A2 to AN and a natural number K. You also have a bag which is initially empty where you can place coins. You need to perform exactly K actions. In each action, you can take one coin from those you have left and put it in your bag. After that, you can no longer take that coin. Um, at the same time, you have a cat that loves even numbers. So every time the sum of the denominations of the coins in your bag becomes even, your cat empties the bag, meaning it takes all the coins to a place known to only to it, and the bag is empty again. Note that the bag is emptied every time the sum becomes even during the process of adding coins, not just at the last moment. Sorry. Let your score be the sum of the denominations of the coins in the bag. Your task is to perform key actions such that your final score is maximized. Find the answer for all k from 1 to n. Okay. So they are saying that what we have here is like we have some coins A1, A2, A3 up to AM, right? And what we can do is we can select some coins, like for a given k, we can select some k coins and add them one by one to a bag. Like let's say I select this A2, so I add it to my bag. Then I select this A5, I add it to my bag, and so on. I can select k items, right? But the thing is that we have a cat which loves even numbers. So as soon as the sum of the numbers becomes even, those numbers will be gone. Okay, so the k is wasted. Like these two operations are wasted, right? And finally, we'll be left with only this. Like our score is whatever we are left with finally. Okay, so basically, we have to like maximize our score. We have to choose exactly k elements in such a way to maximize our final score, right? And we have to solve this problem for every k. Like for all k from 1 to n, you have to solve this problem. You have to print n numbers, right? Okay, so that's the problem. So before solving it for every k, let's solve it for some value of k, some general value, right? Like let's just uh, take an example. Okay, so 41312, 41312, and let's solve it for k equal to 3. Okay, now first of all, um, let's say you are inserting some numbers into your bag. Okay, so let's say you inserted an even number, right? Then it is gone. Why? Because the sum would become even if you do that. Like if you keep an even number here, then currently the sum is even, so the cat will take it away. So there is no point in keeping an even number in the beginning, right? Unless you want to waste operations. Okay. So what you will do is you will give an odd number first, right? So the sum is now odd, and the cat won't take it, right? Now what you will do is if you keep an odd, then odd plus odd is even, so the cat will take it. So you will keep an even number, right? You'll give an even number. Sorry. So you will do that. Then again you'll keep an even number. Why? Because if you keep odd, so odd plus even plus odd, that would be even. And so we would waste all our 3 coins, right? So basically you will first keep odd, and then you will keep keeping evens. That's how it works, right? So for a given value of k, you want to maximize your score, right? So of course you will keep the highest values first. So like you will choose the maximum odd number and the maximum even numbers that you can get, right? So for example, if we have k equals to 3 here, we have k as 3 here. Um, so what we'll do is first we'll have an odd number. So highest odd number is 3, right? So we'll keep 3 first. Then we will choose even numbers. So I'll choose the highest one first, then second highest one, right? So for k equal to 3, we can choose these 3 values, and our cat won't take any of it, and the answer is 9. Okay. Now let's say the test case was a bit different. Let's say it was 2. Okay. So now for let's say for k equal to 4, if k was equal to 4, then you can add one more even number, right? You will add one more even number, which is 2, right? So the answer would be 11 for k equal to 4. So you can do that. Like you can simply keep one odd number in the beginning and then keep adding even numbers as k increases in the decreasing order, right? But what if the number of even numbers is now gone? Like what if you have run out of even numbers? Like let's say in your array you have 5 odd numbers and 9 even numbers. Okay, and your k is now 11, right? So in my strategy, what we did was we first kept one odd number, then we kept all even numbers. So 9 even numbers are there, right? But we have one more space now. Like we have to place 11, but we have only placed 10, right? This one odd plus 9 even. So we have to place an odd here. And if we do that, then the sum becomes even, and the cat will take all of it, and our score will be 0. Okay. So we won't do this. Like for 9 even, basically if we have run out of even numbers, then what we will do, that is our only question now. Okay, so what can we do? Sorry. So basically let's say for k equal to 10, what we did for k equals 10, um, we okay, let's take a small example. Let's say we have 3 odd numbers and 4 even numbers, Okay, so until k equal to 5, it is fine, right? Until k equal to 5, we can keep it as odd, even, and even, right? Okay. But as soon as k becomes 6, like for k equal to 6, then what can we do? If we keep an odd number here now, then it will get eaten by the cat, so that's not the point. So instead, what we have to do is, um, see, the main thing here is that there is no way to avoid getting eaten by a cat now. Okay, like my point is that you have only four events, right? You have only four events, but your k is 6. Okay, so you will put at least two odd numbers, right? That is true. But as soon as you put the second odd number, the sum would become even, and so the cat would take all of it, right? My point is, if you have uh, three odd numbers, four even numbers, and k is equal to 6, so of course you will have two odd numbers somewhere in your array, and maybe somewhere there will be four even numbers. Okay, maybe, like, maybe you will have only three even numbers and three odd numbers, but we'll see that later. But definitely you will have two odd numbers, that is for sure, at least two odd numbers. Okay, so as soon as you put these two odd numbers, this entire array is gone. Okay, that is the problem. So your actual thing starts from here. So what you want to try to do is, you will try to minimize the loss, right? Like, let's say if you keep an odd number here, okay, then this entire thing would be gone, right? So you would instead keep the odd number here, or even actually here. You will keep it here, so that this event does not get harmed because of that. So first you will start off with two odd numbers, because you need to have at least two of them. So you will keep two of them in the start only. Okay, so that is true. Like, that is fine. But now what you need is one more odd number. Why? Because if you keep evens now, if you keep putting even, then again, like, okay, here odd and odd, this is gone. Then you put even. So sum is even. So it will be gone. And if you put even, it will be gone. So what you need to do is, you will need to start with one more odd. Like, you put two odd because you had to. Then you will put one more odd. Okay. So, and then you can put rest even. Right? For you have k equal to 6, so you will put three evens. Right? So you can compare. Like, you can compare that for k equal to 5, you had one odd and four evens. Right? But for k equal to 6, what you have is three odds and three evens. Like, um, one even had to go. I mean, there were four evens here, but only three are there now, because one had to go, because you need three odd. Otherwise, the answer is zero. Like, if you keep only two odds, then the score for this is zero. So what you will do is, you will keep three odds here, and then the rest evens. Okay. So I will show you the pattern. Okay, just observe the pattern. Okay. So let's say the same thing. You have three odds, and let's say you have, okay, let's take more odds. Okay, four odds and four even you have. Okay. So for k equal to 1, it is odd, right? You will just keep odd, because it will start with odd, right? Then for k equal to 2, it is odd and then even. Then for 3, it is odd, even, even. Then for 4, it is odd, even, even, even. Right. Then for 5, it is odd, even, 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 and even. And for 6, okay, now you had only 4 evens, right? So they are all used up now. Okay. So now what do? Now you will keep 3 odds and 3 evens. That is, you will eliminate one of these evens. Like, okay, you are inserting in the decreasing order, right? Like this is the largest E, then second largest E, third largest E, fourth largest E, right? I mean, this is the smallest E because there are only 4 E's. So fourth largest E means the smallest E. So when you are going from for this 5 to 6, you are excluding this E, right? And okay, so until here, like here the score is this odd number. For k equal to 2, the score is this plus this. For 3, the score is this plus this plus this. For 4, score is this. For 5, the score is this. But for 6, the your score is just this, right? Because these two odds have been eaten up by the cat, right? Now for k equal to 7, for 7 again you can like insert that e again. This one which you remove, you can insert it again. So zeros like o and e, right? So here again the score becomes this thing. Okay. And for 8, uh, you have no other choice. Actually, ideally, what would you do? Ideally, you would want this, right? That 5 O's and 3 E's, right? You will eliminate this E and add 2 more O's so that your score would become this. You would want this, right? But actually, um, when you reach this 8, that is, the string length is 8 only, right? The array length, the total 8 numbers. So n is equal to 8 in this case. So when you reach this 8, actually your entire thing is over. Like you don't really have 5 O's to insert, right? You have only 4 O's. So the best you can do is like you can actually not do anything because the total sum is even for this, right? If you have 4 odds and 4 evens, then total sum is even, right? Because 4 odds means 4 into some odd number, so it is even, and 4 evens means that is even. So if you add them, it is even. So basically, like as soon as you insert the last number, like whatever you do for k equals to 8, for k equal to 8, whatever you do, whatever, as soon as you insert the last number, the sum would be even, right? So the cat would take all of it, and the answer would be 0. So for k equals to n, it is something different because we are forced to do that thing. But before that, we can do it like this. Okay. But yeah, if for k equal to n, if the odd numbers is odd, like here, the number of odd numbers was even, right? So the sum was even. So for k equal to n, the answer was 0. But if the total sum is not even at the end, like let's say we have 3 odd numbers and 4 even numbers, okay, or let's say just 2 even numbers, okay, and let's draw the table now. So for k equal to 1, we have odd. For 2, we have odd even. For 3, we have odd even even. For 4, we have to eliminate this even. So 3 odds and 1 even. And then for 5, we can insert the even. Right. So here for 5, the score is this. Okay. Whereas if there are odd number of odds, then the score is 0. Okay, so there are two cases for k equal to n. If the sum is odd or sum is even. Okay. So this if the sum is odd, then for k equal to n, the answer is just all even numbers plus highest odd number. Right. And otherwise it is 0, right? And for k equal to 1 to k equal to n minus 1, you can just follow this pattern. Like just insert an O initially, then insert all the E's that you have, okay, in decreasing order, okay. Then as soon as you run out of E's, what you will do is like your score will decrease by 1. I mean, see what I'm doing is I am inserting an E at every step. But as soon as you run out of these E's, like as soon as these E's get over, the next score is this. So it is basically this score minus this E, right? And after that, the next score is this score plus this E. Okay. So you can like see the pattern and code accordingly. Okay. So like I'll show the code. In fact, I'll code it in front of you because my code in the contest was pretty bad. It was pretty complicated. So I will code this in front of you right here. So I'll take int n. Okay, let's do it in LL because everything is in LLN, C in N. Take the input and separate the array into even and odd. Okay. So if AI is odd, then O dot pushback AI, else E dot pushback AI. Then what we'll do is, okay, if first of all, if there are no odd numbers, like all are even, if E dot size is equal to N, then the answer is just 0, 0, 0, 0, right? Because you will, at every step, you will place an even number and the cat will steal it. So the answer is just N zeros. So I'll see out 0. Right. And if there are no even numbers, that is every odd number is there, then your answer is just basically if you place one odd number, if you put one odd number, it is fine, your score is that. If you put two odd numbers, then your score is 0. If you put three odd numbers, then your score is the last odd number that you placed. Okay. If you put 4, then again your score is 0. If you put 5, then these two would be taken, these two would be taken, and the last one would be your score. So basically, at the odd k values, the last one would be your score, and at the even k values, it would be 0, right? So you would choose this to be the largest odd number. Like you would choose the largest odd number here. So what I'll do is I'll sort both E and O here. Dot E and O dot N. Right. And if O dot size is N, that means all odd numbers. So for int k equal to 1, k less than equal to n, k plus plus. If k is odd, then print the maximum, like maximum odd value, right? Otherwise, see out 0, right? And then just print the new line and return. Okay, so we have these two edge cases. If all even numbers and all odd numbers, okay. But if we don't have that, then basically your score would be the highest odd number initially, and you'll print it. Like for k equal to 1, it is the highest odd number, right? Now for in k equals to 2, k less than equal to n, k plus plus. So if you don't have an even numbers, if e dot size equal to 0, that means you have used up all of the even numbers, right? You are basically at this point. Or I'll keep an answer vector. Vector of int ans of n plus 1. So ans of 1 is basically the score, right? Yeah, now basically if you have run out of even numbers, that is you have done this, then you are at this step right now. So you have no more even numbers to insert. So in that case, the answer is just the answer of I minus 2. Like this O and 3 times E, it is same as O and 3 times E, right? And same for this, the answer is just this answer right here. Okay, so you can simply take the answer for I minus 2. Okay, so if E dot size is equal to 0, then ans of k equals to ans of k minus 2. Else, ans of k is equal to ans of k minus 1 plus E dot back. Like just um, insert the next highest even number and E dot pop back, of course. And then for int I is equal to 1, I less than equal to L, you can simply see out the ans vector. Okay, so I wrote this code right now because my code was pretty bad. It was not what I explained. So let's see if it works. Okay, it does not work. Yeah, because as I told you, for k equal to n, you have to do it separately. Okay, so I'll just loop this until n minus 1, right? And for k equal to n, so if the sum a comma a plus n comma 0 l is odd, like let's just store it in sum, or okay, if it is odd, if the sum is odd, that means okay, if the sum is even, then your score is 0. I mean ans of n is 0, and if it is odd, then it is just um, this thing. So it is just ans of n minus 2, right? So in that case, it is well. Like in that case, it works if the sum is odd. Okay. So now let's run it. Okay. So it is still wrong on this test case. Let's see what is the problem. 412. Okay, yeah. Because basically I have enough even numbers. Like this pattern of n minus 2 hasn't even started. Right. So for that, um, let's see. Or let's just do this. Like let's just run this till n and check if the sum is even. So if sum is even, then we'll change it to 0. Otherwise, it is the same. Okay, so this should work. Yeah, this works, I guess. Let's um, submit this. I guess it is something about int and ll. Yeah, vector of ll. How much? Okay. My bad. This is the kind of mistakes that you do in contest and get a penalty. Okay, it will pass, I guess. I guess it will pass. So I hope it is fine. Nowadays, solving three problems in an hour is same as 800 rated. Well, yeah, I guess cheating has increased very much. So that is pretty sad. So like at this point, I just do CP for fun and not for rating, because I know that um, the real rating is not this one. But I just like to solve problems, so I do it. But if you want like good rating for internal placements, then it is a different thing. Like that is a harsh reality that cheaters have messed this up. But what will we do? Anyways, so C was this was C. If you have any doubts, then you can ask right now. Any doubts in C? Okay, I guess there are no doubts, or maybe the messages are not coming. I'll check on YouTube. Okay, there are no doubts, I guess. So I will move ahead with D, which is Fibonacci paths. You are given a directed graph consisting of n vertices and m edges. Each vertex V corresponds to a unique number AV. Count the number of distinct simple paths consisting of at least two vertices such that the sequence of numbers written at the vertices along the path forms a generalized Fibonacci sequence. In this problem, we consider that the sequence of the numbers x0, x1, xk forms a generalized this sequence if x0, x1 are arbitrary natural numbers and xi equals to x of I minus 2 plus x of I minus 1 for all 2 to k. So basically, um, we want that we want to count the number of paths. Like we have been given a graph, okay, a directed graph, and we want to count the number of paths in this graph such that, let's say, like the nodes are numbered, right? There's a number for each node, a1, a2, a3, and a4, right? So whatever our path is, a simple path, we have to count all like the number of paths in this graph such that it is a Fibonacci sequence. It is a Fibonacci sequence. Like let's say the path is b naught, b1, b2, b3, right? Then these two can be anything, b0, b1, but b2 has to be b0 plus b1, and b3 has to be b1 plus b2. Okay, so this is how the path should look like. Like if you want this path to be a Fibonacci path, then these two conditions should be satisfied. Okay, so you want to count the number of paths. Count the number of such paths. Okay, so actually this kind of looks like a DP kind of thing, right? Like if you have done some deeper graph, then you might think about recursive things, right? Like if you want the number of paths, let's say if you want the number of paths, like let's say we have a graph like this. Okay, And if and like you want the total number of paths, right? Then you can, let's say, count that for every vertex v, you can count the number of paths ending at that vertex v, right? And then maybe you can sum them up, right? Like let's say you want to count the number of paths which end at this vertex, okay? And let's say there's one more edge like this. So there are two edges incoming to this node. So like let's say you want to count the number of paths ending at this v. So either um, it is the only v, like the path is just this v, or maybe the path, like all the paths that end here, and you can insert this node in front of them. Like just consider all the paths with which end here, right? And then you can append this node in front of any of them, right? So let's say there are x paths which end in this node, then there are x paths which end in v as well, because you can simply append v to any of those paths, right? Because there's this edge. Because of this edge, you can insert v in front of the all of these paths, right? So one is this just v, or you can have x paths from right here, or maybe if there are y paths which end in this node, then you can append v onto them as well. So there are y paths more. So the number of paths ending at this v is 1 plus x plus y. Now you might think that is a cycle. Like since there's a cycle, so the number of paths ending here depends on this one as well. So that is true. Like I drew this wrongly. Like I should have drawn a DAG. Okay, like a graph with no cycles. Okay, so in that case, this would work. Like if our current problem was to just count the total number of paths in the given DAG, right? Then you can simply use DP. That's my point. Like you can simply use DP to count the number of paths in this DAG. Okay, but like why am I telling you this? I'm telling this because you can simply think about DP in this one as well. Like in the problem D, that's how you can get an intuition about DP. That you can try to recursively find the number of paths. Okay, so let's say you have a path. Like basically what you want to do is you want to transition, right? Like in this problem, count the total number of paths in a DAG. So in this problem, what you simply do is for every node, count the number of paths, right? For every node, you count the number of paths recursively. Like if you want the number of paths for this node, then you can simply count the number of paths for this and the number of paths for this, and you can append this node to any of those paths, right? Because there is these two edges. So basically the DP of this node, the DP of this V is just x plus y. If this is x and this is y, so x plus y is the answer, right? So you can append, and that is because you can append this node to any path ending at here or here, and it would be valid, right? But in our problem we need to count the number of Fibonacci paths, Fibonacci paths, and not just the total number of paths, right? We need to count only the number of Fibonacci paths. So like let's say you have a path, like by the same logic, let's say you have a path Like, okay, let's say for this node, you want to calculate that what is the answer. Okay, the number of Fibonacci paths ending at this node. You want to count that. Okay, let's say you want to count that. But you can't do that directly, because like if you know the value of this x and the value of this y, that is, you know that what is the number of Fibonacci paths ending at this node and also at this node. So you can't really say that the answer for this would be x plus y. Actually, in the above thing, it would be x plus y plus 1, right? X plus y plus 1, because this path, like plus 1 for just this node, right? Okay, so yeah, in here you can't say it would be x plus y plus 1. First of all, plus 1 you won't do, right? Because we need only the paths of at least length 2. Path of length greater than equal to 2 we want. Okay, I mean at least 2 nodes. The path should have at least 2 nodes, right? So we won't add plus 1 here, first of all, and second of all, we can't say that it is x plus y, because let's say these y paths, they are all Fibonacci, right? But if I add this node to that path, then what is the guarantee that it remains Fibonacci? We don't know, right? That what is the sum that is required. Like let's say the path was something like 2 to 1 to 3 to 4 to 7. This was the path ending at this node. Like this node, the number was 7, and this was the path ending at this node. So we don't know, right? That like if this node is 11, then only we can insert it into this path, right? Otherwise, we cannot insert it into this path. Like we won't count this path when we're counting for the path ending at 11, right? So we need to know that in our path, what were the last 2 nodes? That's the main thing. Okay, like we need to know that in our path, like in these y paths, I want to know that actually, like, see, currently I am giving my state as dp of v, like dp of v, where dp of v is number of paths ending at node v, ending at node v, right? We are giving that state, but I am saying that it is not enough information, because it might happen that some paths ending at node v might be compatible. Like we can insert this node at the end of that to get one more Fibonacci path, and some nodes might not be compatible, right? So actually we need to store more information in the state. Like this state of the node is not enough. We actually need the last 2 nodes. Okay, like if we know that what was the last node and the second last node, then we can compute that what is the sum, right? Like if we know that what is the last node and second last node, then we can find out that what is the sum. And if our sum matches, like if that is the number that we have on this node, then we will count those paths. Otherwise we won't count those paths. So I'm keeping a dp like this, that dp of u comma v is the number of Fibonacci paths which have last node as v and second last as u. Okay, so instead of just dp of v, I am storing dp of u comma v, where u and v are nodes. Okay, so the number of Fibonacci paths which have last node as v and second last node as u. So I'm keeping that dp. So now if I want to transition, I can simply look at the outgoing edges of v. I can simply look at the outgoing edges of v, and for whatever nodes I have the matching number. Like I want to have a of u plus a of v, right, in my next node. So I will check all the nodes which have that number, and I can propagate my dp, right? But you might think that this dp state is of n square, right? Because this you can have n possibilities and we can have n possibilities. So O of n square. So I have an n square dp, but the limit on n is up to 10 to the power 5 or 2e5, right? So how does it work? Will this work? Any ideas? This dp is n square, right? Or is it not? Will this work? No. Okay, so actually, it will work. Why is that? Because see, what I am saying is dp of uv is the number of paths which have second last vertex as v, as u, and last as v. That is, you have like all the paths like this, where second last node is u and last node is v. So that means we have to have this edge from u to v, right? Basically, we are storing the dpu only for all the edges, right? Like for my dp of for my dp a comma b, for this to be a valid state, or basically for it to be non-zero, I have to have this a to b edge, right? So essentially it is not order of n square. I mean, it is order of n square, but actually you can say that it is order of number of edges as well. Like if you have m edges in the graph, m edges, then actually this dp is order of m only, because the number of pairs u comma v are like u comma v is only valid if there's an edge u to v. Okay, and that is order of m and not order of n square. I mean, it would be order of n square if the m could go till n square, but like order of m works, right? Because the limit on m is given to be 2e5, right? Yes. So essentially, you can think of it like dp of u comma v as the number of Fibonacci paths which end in like second last vertex is u, last is v. So you are saying that we are doing 2D dp on the vertexes, right? But actually, I can say that we are just doing 1D dp on the edges. Like essentially, I can rewrite my dp as dp of uv, or let's say dp of I. So my dp of I will store the number of paths um, ending at edge I. Like basically, instead of storing u and v, or actually I am storing u and v only, so let's do that only. Like basically, yeah, um, my dp of uv, um, my dp of u comma v stores the number of paths ending at edge u comma v. Okay, so this is my state. All right, and the transition is pretty simple. Like you can simply transition very easily. How you can do that? Let's see. Okay. So first of all, I'll use a push DP here. Okay. Like I will see that if I have a path, if I have a path which is Fibonacci and it ends in the edge u comma v, then I will like try to add some vertices to this path to make a new state v comma x, right? And I will just do dp of v comma x plus equals to dp of u comma v, right? So for every uv, I will look at what the like what nodes I can go to, okay, and then I'll do this, right? So kind of I have a push dp here, okay. So all right, so like now for a given uv, like for a given state, where can I go from this state? So basically, I can only append those nodes which are having an edge from v to x, right? Like all the neighbors of v. I mean, all the nodes for which there's an outgoing edge from v to x. So all those nodes x, I can update. But there is one more condition that a of x has to be also equal to a of u plus a of v, right? So basically, I will update all of those, like I will update dp of v comma x plus equals to dp of u comma v for all those nodes x such that ax is equal to au plus av, right? So basically, if I have the dp value of u comma v, I can use that to like I can propagate that to v comma x, where this ax should be equal to au plus av, because I want that the path to be Fibonacci, right? Like here I have au, here I have av. So for Fibonacci, this has to be au plus av. So I can only append those nodes x which have au plus av, right? So actually, to optimize this, like how would you transition? Like let's say you are looping over the edges. Like let's say for a particular u comma v, you are checking all the neighbors. Like for auto x in adjacent of v, right? You are doing that if a of x equals to a of u plus a of v, then you are doing dp of v comma x plus equals to dp of u comma v, right? But if you do this, it would iterate through all the neighbors of v, even those which are not ax. Like let's say I have this u, I have this v, and v has multiple neighbors, right? And only some of them have the value of au plus av. So actually, for each edge, I am going through all of them. So that is inefficient, right? Like that might lead to TLE. So what I'll do is I will store these vertices value wise. Like instead of vector, right? Normally what we have is a vector of vector for adjacency list, vector of int, right? That is for every node we store a vector which stores the all of its children, right? But what I'll do is I will have a vector, like for every node I will store that for each value. So I will map for each value what children are there. Okay. And I will only iterate through those children when I'm trying to like update. Like for UV, instead of doing auto X and adjacent of V and then checking if its sum is matching, I will do auto X in adjacent of V comma AU plus AV. Okay, so basically all the vertices which are adjacent of V and which have value of AU AV, and then I can simply update that, right? Okay, guys. And actually the main thing to, so like, so there are two things right now. Okay, like there are two things remaining for me to tell you. Okay, so the first thing is that, okay, we figured out how to transition. Like we figured out that what is the transition, right? But um, like how do we actually do it? Like in what order? The main question now is, in which order do we update the DP? Because when I am trying to push UV, like from a, if I try to go from a state UV to a state VX, I have to know the value of UV first, right? So in what order do we transition to ensure that this holds? Like in the board, let's say in the grid DP, right? So in grid DP, you know, right, that let's say if the DP value of some cell depends on its left one and its above one, then the DP value of these two has to be calculated before the DP value of this, right? So you would normally just go like this from left to right, right? So in this order you can do. But in our case, what should be the order in which we do the DP? What is the order? That's the next question to answer. So if we are transitioning from UV to VX, then actually I can say one thing for sure. That is, let's say the value of this edge is AU plus AV. Okay. And the value of this edge is AV plus AX. Right. So I can always say that for our graph, like our for Fibonacci sequences, this will be true. That AU plus AV is always less than AU plus AX. Why? Because AX is AU plus, like the value of AX is greater than AU, right? Value of AX is AU plus AV. Okay. So that's why I can say that if I'm transitioning from this edge to this edge, like from UV to VX, if I'm going, then definitely the value of this edge will be less than this edge. Okay. And so simply I can find out the value of all the edges. Okay. I can find the value of all the edges and make the DP in increasing order of that value. So like whenever I am transitioning from UV to VX, I will know for sure that this UV has correct value, because anything that can transition to it must have a lower value, and I must have uh, added that to UV because I am going from lower to higher. Okay, so that's the entire thing. So in that order, like basically, if the edge is U comma V, then in the increasing order of AU plus AV, you can make the DP, do the DP, right? That's one thing. The order of transitions, right? But what about one more thing? Okay, I'll tell you one more thing, but before any doubts, yes, I'll use map. Yes. So until here, do you guys have any doubts? like in the DP or the transitions or the order. No? Okay. So there is one more caveat. Like, okay, what I did was I thought this was the entire thing. Like, whatever I told you till now, I thought that was the entire solution. And then I submitted it. Like, I submitted that and it got TLE on test 11. Okay. So I thought, why is that happening? So, um, what I figured out was actually I was missing one thing. Like, my transitions were like this, right? Like, what I was doing is if I'm transitioning from edge u comma v, okay, then what I did was x in um, for x in adjacent of v, comma au plus av. So only those nodes which have value of au plus av, I am doing dp of vx plus equals to dp of uv, right? So this was my for loop. Like for this uv, I am doing this for all the x. Like basically, I have this edge u to v, and then I have this edge v to x. Okay, so I am transitioning. I am giving the value of this edge to this edge. If this value x is correct, the ax is if this ax is correct, then I am giving this value from this to this, right? But the problem here is that um, this edge might come multiple times for different uv. Like I'll give an example. Let's say we have this graph. I have the value 1 here, value 1, value 1. Okay. And then I have the value 1 here as well. Then I have value 2 here. I have value 2 here and value 2 here. Okay. So what will happen is first I'll look at this edge. Like, okay, I'll sort the edges in the order of u plus v, right? I mean, au plus av. So for these edges, it is 2, 1 plus 1. And for these, it is 3, right? So what I'll do is I'll sort them. So I'll deal with this first. So initially the dp value is 1. Like I'll add the dp value of this to all these three edges, right? This edge, and this edge. Why? Because all of these three nodes have the correct sum. Okay. So then I will look at this edge, and again I will add its value to here, here, and here. And similarly for this edge, I will add its value to here, here, and here. So basically, if you have a graph like this, like just imagine a graph like this with m by 2 edges here, like m by 2 edges here and m by 2 edges here. So for each edge here, you are adding into each edge here. So that is m by 2 into m by 2, which is O of m square. Okay, that's the issue. So even though we are only checking the nodes which have the correct value, like I'll discuss that, right? That I am storing it value wise, vector of map of int comma vector of int, right? So even though we are doing that, but still it is not fast enough. Still it is order of m square in the worst case, right? So to optimize that, what I am doing is I am transitioning value wise. Like see, um, the problem occurs only when multiple incoming edges have the same value. Like this one has 2, this one has 2, this one has 2. So all of them are trying to call to all the twos nodes. Like the problem is that all these three edges have same value, so they are calling these nodes with same value multiple times, right? So to solve that problem, what I did was, first, like, let's say the dp of this edge was x, the dp of this edge was y, and this was z. So instead of doing x plus y plus z on this edge first, then x plus y plus z, I mean, sorry, what will happen is, this x will first go to all these three. So x and x हो जाएगा. Actually, initialized, they are initially one, right? I'll talk about that. They are initially one. So when x is added, it becomes 1 plus x, 1 plus x, 1 plus x. Then y would be added to all three. So 1 plus x plus y, right? And then z would be added. So 1 plus x plus y plus z, right? So instead of that, um, see, initially it is 1, right? What I'm doing is, I'm adding x to this node. Okay. So x, like, all these three edges have a value of 2, right? So right now I'm dealing with all these of value of 2. Right now I'm dealing with all the edges with a value of 2. So these three edges. So what I'm doing is, I am adding up their dp value into this node. Okay. Like, let's say x, then this y, so x plus y, and this z, x plus y plus z, right? And then as soon as I am done with these two value edges, I can transport this value onto all these three edges. Like this single value, I can transport this into all these three edges. So basically I did m steps here, like one step, two step, three step. So m steps here, and m steps here. So order of m complexity is satisfied. Like basically, I am not updating the dp. Like what I did was, I did not update the dp of these three edges um, directly. Like first, like basically I knew that these three dps, this one, and this one, it is correct value. Like I know that it is correct because this is the lowest, right? Like all of these three are the lowest, 2, 2, and 2. So I know that all of these three are correct. So I just together move this value to this node, right? And from this node, I moved it to all the edges. Like I just moved the sum. Like I added up the values in this node, and from this node, I moved it to all the edges. Okay, and that's how I can do it in O of m. Okay, so is this kind of clear? Like what was the issue and how it solved it? You mean the code? I'll show the code, but before that, is the logic clear? Okay, and for the others, I'll give a summary. Like summary is that my dp of u comma v is the number of paths, number of Fibonacci paths ending in edge u comma v, right? So we can transition from uv to vx if and only if the value of ax is equal to au plus av, right? And also there's an edge between x v to x. Okay, so we can transition like this, and we also saw that this transition will only happen from an edge of a lower value to a higher value. Like the value of this edge is au plus av, and this edge is av plus ax, and this ax is the same as au plus av, so this value is larger. Okay, so it will only happen from smaller to bigger edge. So we can simply sort the edges in ascending order, and we can do the dp, right? And yeah, also one more thing, the base case. The base case is that um, like for if we have an edge uv, then this by itself is a path, like just au comma av. This is a valid Fibonacci path. So for all edges, the dp value would be 1. dp of all edges would be 1 initially, because that edge just by itself is a Fibonacci sequence. Okay, so that's what the logic was, and I'll show the code. So the code is pretty bad, but I'll explain it. So I have this adjacency list, which is map of int comma vector of int. Like for each node, I am storing that for each value, what are the indexes of the nodes, right? Then I have a map of dp. So map is from pair to modular integer. Like this mint is just a struct which has all the operators overloaded. So it automatically takes the mod. Okay. So I have this dp array basically. So dp of uv would store the number of edges which have dp of uv would store the number of paths which end in the edge uv. Okay. And I have this edges vector, which is a ll comma pair of ll comma ll. So basically this ll is the value of this edge, that is au plus av, and this is the actual uv. I am using this to sort the edges, right? So I will take the input int ab c in ab, do it zero based indexing, and dp of ab is equal to 1. Okay, right? And edges dot pushback va plus vb, like I'm calling it v instead of a. Okay, and comma ab, right? And also this adjacency list. So adjacency of a comma value of b dot pushback b, right? Since edges from a to b, so adjacency of a dot pushback b, but in which one? The value of b1, right? Then I'll sort the edges. Okay, and then um, okay, I sorted the edges, and yeah, then what I did was I grouped the edges value wise. Okay, like I had this edges, right, where I have value comma pair, like the value comma edge, right? So I just grouped them in this map value wise, like value comma vector of pair. So basically for a certain value, what are the edges having that value, right? So I can treat them group wise simultaneously. Like here we saw that all of these edges had a value of 2, so they would be in the vector of 2, right? So in this temp I am storing the group wise edges. group by value, group by the value, right? So basically for auto sum comma p in edges, temp of sum dot pushback p. P is the pair, like u comma v, right? And then for all the groups of edges, like let's say for a particular sum, I have a vector of edges, right? Temp. Like I have a vector of edges. Um, so I will like store basically for all the edges in that group for auto p in vect. This v is p dot second. That is the final node. So I am storing in that final node the value of dp, the dp of p. Okay. So here let like basically if you can see, I am storing this value of x into this final node right now, and this value into this final node, and this value into this final node, right? And then so this loop does that, and then for all the nodes that I stored the value, I will iterate through their children, having that sum which I'm having right now, dealing with right now, right? So like from this vertex, I will find all the children which have the number 2, right? So for auto y in adjacent of x comma sum, dp of xy plus equals to val. So for all these edges, for this edge, for this edge, and for this edge, I am adding this val right here. Okay. So this is how I can do it in order of m instead of m square. Like initially I wrote this code, and this one is m square. Okay. So इसको हटा के I put this, so it is order of m now. And finally the answer is just the sum of all the dp's, right? Because our path can end in any edge, so I'll just add the dp values and I'll print that. Okay. Using dfs, um, I think you can simply do it like, yeah, like let's say you are at a state, you are at a state of um, au comma av, like you are at an edge u comma v, right? Then you can simply do for auto x in adjacent of v. Okay. um, if that, like I think one of my friends has done it using uh, dfs, so I'll just open that code. Yeah, so what he did was in his dfs he has the node. Okay. So like he is doing dp on the nodes and not the edges. Okay, sorry. Okay, so it's like his dp is somewhat different. His dp stores that um, what is the last node comma what is the sum of the last edge, right? Like he is storing last node comma sum of the last edge. Okay, and basically the main thing is here that when he is iterating through the childs of the node, if value of child is less than equal to the value of node, then continue. That is, you don't do DFS there. You will only go like from a particular node. You will only go to those children which have a value higher than that. So if a of child is greater than a of node, then only you will go to that child. Okay, and then you will update DP of node comma a of child. Okay, so node comma a of child. So this means the DP is something like the second last node and the last value. So like I think you can look at this code and try to understand it because the states are a bit different from mine, and I'm not sure how to do it using DFS in my code. Okay, but I think mine is also pretty simple, right? This is pretty simple to understand also. But if you want, you can look at this code. From where should I learn DP? Um, like personally, what I did was I looked at this YouTube video. Okay, so there is this playlist by Priyat Shagrawal, and he teaches the DP. So, like this video is for intro to DP. Watch this one to get a hint about what is DP. Okay, and then as he told in this video, I solved the problems on CSCS. Okay, so CSCS DP section, I solved it one by one, and then I saw the solutions from this. Okay, and that is how I started. And then I did some problems from Codeforces, like from CF problem set. You can simply pick up some problems, uh, like add tag and DP, and whatever rating you are comfortable with, you can add that, and then you can simply solve. You can simply practice that DP from there. So yeah, the main is CSCS plus practice from CF Codeforces. And if you still are struggling, like you can maybe find some patterns on lead code or like the DSA courses, right? So you can maybe find some pattern, but in CP that won't help. Like in code forces contests, those patterns won't help because um, they never come. Okay, so for CP you have to practice only from problem set and CSAs, and also the ad coder DB contest is also nice. This is also something that you can practice. Okay. Anyways, so let's move on to E now. I hope D was clear. So let's move on to E. Okay. So problem E was remove the lowest cost. You have n elements. Each of these elements have a natural value AI and a natural removal cost CI. You need to remove all the elements except one, paying the minimum possible cost. To do this, you perform the operation n minus 1 times. In one operation, you choose two adjacent elements and remove the one with a smaller value. For this operation, you pay the removal cost of the least expensive element among the two. If these two elements are equal values, you can remove either of them, paying the removal cost of the minimum of the two in terms of removal cost. After removing an element, the elements go to the right of the removed element. Sorry, after removing an element, the elements to the right of the removed element shift left by one, leaving no gaps. Okay. So basically, you have two arrays. Like you have n elements, and you have a value array, and you have a cost array. Okay. So let's say you have 5, 3, 2, 4, 1, 2. Okay. So what you can do is you can select any two elements and delete the one with smaller value, and the cost is the minimum cost. Okay. So via the cost of 3, you can delete this element. Okay. So and then the this value shifts here. So it becomes 5, 3 and 1, 2. Right. Sorry. And then you can select these two. So this has a lower value, so it will get deleted, and at a cost of the minimum of these two. So cost would be 2. Right. So initially the cost was 3, and now it is 2. So 3 plus 2 is 5. So you took 5 cost to delete n minus 1 elements out of these n, right? And finally only 5 comma 3 remains. Okay. So that's what you can do. And you want to find out that given this value array and the cost array, you want to find out that what is the minimum possible cost to delete n minus 1 elements. Okay. But actually this was too easy for them, so they said that you have q queries also, like you have queries also, that basically in the is query make cost of pi equal to 0. Like initially they have given some value and cost array, right? They have given this value array and cost array. This is the value array and this is the cost array. So we have to print the answer is 42. Then they are saying that make this cost 0, like make the first cost 0. So we make this 0, and then we print the cost, which is 36 now. Then they are saying that make the cost 10, make the cost 10 0. So we make this 0, and then we print 30. Right. So they have given this permutation, and like after every update, we have to print that what is the new cost, like what is the new answer. Okay. So we have to give n plus 1 answers, and every answer is the minimum possible cost to delete n minus 1 elements, right? But every time the array has changed. Okay. So how do we actually solve this? Now I don't have the formal proof of this, like my method which I have followed. I don't have a formal proof of why it works, but it is quite intuitive. Okay. So let's say we have this test case. I'll copy it. Okay. So we have this. Now, okay, this is not very good. Let's change it a bit. Okay, I think now it should be better. Yeah. So this is our test case. Okay. And so here what you will see is this is the cost. This is the cost, and this is the value. Right. Now you can see the minimum value, like the minimum cost in this thing is 3, right? There is nothing less than 3 in these two arrays, right? So the minimum is 3, right? Now if I ask you, like, okay, the operation that was given to us, like in the operation, we can select two adjacent indices, right? And we can delete the smaller value. Like whichever is the smaller value, I can delete that at the cost of the smaller one, right? So I can delete this 4 at a cost of 6, right? Because this 4 was less than 10, right? But let's say it was more than 10, let's say it was 11. Then I could not have deleted this 11 via this 6. If I want to delete that, I would have to take this 9 cost, right? So basically, since this 10 is greater than or equal to 4, I can use this 6 to delete this 4. Okay. Similarly, I have this 3 right here, correct? So since this 5 is equal to this 5, I can use this 3 to delete this pair. Okay. So I can delete this pair using a cost of 3. Then I can delete this one. No, I can't, because if I choose these two, the smaller one is 5. Okay, so I can't delete this one using 3. Okay, so using this 3, I can delete these two, right? So for these two, the cost of deleting would be 3. Okay, then let's say this is also a 3, the second minimum value. So for this value, the cost of deleting for this it is 3 also. But you can even go one step further. Like for this element also, the cost is 3. But for this element, you cannot say that, because 5 and 10 mein 10 is bigger. Okay. So you cannot really use this and this. Like you will say that, okay, maybe uh, delete this pair, then these two are adjacent, and then delete this pair using this 3. But you can't do that, because this 5 is less than this 10, right? So basically using this 3, you can only go as far as the numbers are less than equal to 5. Okay, as soon as the number is greater than 5, you can't go there. Okay, so basically you can delete these two elements using the cost 3. Okay, then what is the next smallest? It is the 6 right here, right? So for this 6, you can actually delete all the elements using this 6, because the value is 10 here, right? The value is 10 here, and all of these elements are less than equal to 10. So actually you can delete all of these elements using this 6. You can delete all of these elements using this 6, right? So basically you got the cost of deletion for all the elements, right? In this way, you got the cost of deletion of all of the elements. Like if you want to delete this element, it will cost 6. For this element, it will cost 6, right? So now what is the total cost? It is just sum of them. But actually you need to delete only n minus 1 of them, right? Like you have to delete only n minus 1 of them, n minus 1 of them, not all of them. So which one should you leave? Like what you will do is you will delete all of these 3 ones. So 12 cost. Then you have 6 numbers left, which cost 6, and you will delete 5 of them. So 5 into 6, which is 42. So like you will leave any one of it. Like in fact, it will be this one only, because using this and this, you will keep deleting that. Like first you will delete this one, then you will delete this one, then you will delete this one. So finally this pair will remain. But the point is that since this 6 was the highest, you did it that way. Okay, like simply my point is that you have simply calculated the minimum cost of deletion of each element, kind of. Okay, and you have to choose n elements to delete. So what you will do is like your final answer is just the total sum minus some element which you won't delete, which is of course the maximum element, maximum cost, right? So sum is what? 3 into 4, which is 12, plus 6 into 6, 36, which is 48. So 48 minus max cost is 6, so which is 42. Okay, so the answer for this is 42, right? So here comes 42. Now they are saying that change this first cost to a 0, right? So they are saying that we need to change this number into a 0, right? So I have to change this to a 0. So I'll use a white pen or a black pen to hide this. Okay. So we have made this cost as 0, right? So actually now I can try to update this 0. Like see, initially my costs are like this, right? 3, 6 and 3, because of this 3, this 3 and this 6. So like this is the area of this 6, this is the area of this 3, and this is the area of this 3, right? But when I do it 0, like when I make a cost 0, then of course the minimum is that only, right? Because initially all were positive. Initially all the costs were positive, and now I have made this one 0. So actually I can say that whatever is the region of this 0, at all of those points the cost would be 0. Okay, like say for this index we can delete this one using this, right? Because 5 is equal to 5, like 5 is less than equal to 5, right? So we can delete this index. So the cost for this one is also 0, and of course the cost of this is 0, right? But this 8 we can't delete using this element because this 8 is greater than 5. Okay, so for these two elements the cost now becomes 0. Okay, so we can simply find again the sum minus max cost, right? uh, yeah, so here sum would be what? 6 into 6 for 36, plus 6, which is 42. 42 minus maximum, which is 6. So 42 minus 6, which is 36. So there is 36, right? Then we convert 10 to 0. Like we convert this one to a 0 also, right? So for this index, its region is this one, right? Basically, the region is like, let's say I am at some index. So its region is until that index where the value is less than equal to that. Like if I am at 4 here and I change this to 0, okay, then um, this 0 can change these 3. Like basically from index I can go to that index j if all the elements between I to j are less than equal to the value of I. Okay, that's my point. So like let's say if we make this one 0, if we make this one 0, then the cost for these 3 elements would become 0, right? And so this is how you can keep, like update the costs and find the sum and the max cost, and using this formula sum minus max cost you can find out that what is the final answer, right? But now the question is how to do it efficiently. Okay, but like did you guys get it why it is correct, like at least intuitively? Thanks. Like until here, do you have any doubts? Like my idea was that for each element you calculate that until which index can you use it to delete. Like, of course, you would try to delete using the minimum cost, right? Like, you want to minimize the total cost, so you would try to delete using the minimum cost. So here the minimum cost is 3. So which indices can you delete using this 3? It would be some array, like it would be a subarray which contains this 3, right? So basically it is this subarray which has a value of 3. Like the cost of deletion for this subarray is 3, because this 5 is less than equal to this 5, but this 8 is greater than this 5. So we cannot use this 3 to delete this 8, right? So for in general, let's say you can delete actually anything using this 6. Like using this 6, you can delete anything, any element, because this is 10, and every element is less than equal to 10 only. Like all these elements are less than equal to 10, and these also are less than equal to 10, right? But you will start with a minimum. Like you will try to do it with 3 first, right? You will do it with 3. So these two elements get the value of 3. Then these two elements also get the value of 3. And then this like next minimum value is 6. So all of these elements get 6, right? And then when you are changing to 0, let's say you change this one to 0. Okay. So you can use this 0 value in these 3 indices, because this value is 4 and these two are less than equal to 4. So the answer for these values becomes 0, right? So these are zeros. This is a 6, this is also a 6, and here it is 3, and here it is 3, right? So what's your sum? Sum is 3 into 2 plus 6 into 2 plus 0 into 3 plus 6 into 1 plus 3 into 2, right? 3 into 2 plus 6 into 2 plus 0 into 3 plus 6 into 1 plus 3 into 2, which is uh, 18 plus 24 plus this 630. And the maximum element is 6. So 30 minus 6, which is 24. So 24 would be the answer if we convert this 9 to a 0, right? So this is what the strategy is. But how do you actually compute this efficiently? Was this no for any doubts, or was this no for do you get it or not? I hope it is for any doubts, like no doubts you have. Okay, okay, cool. So the algorithm is this, but how do you actually implement this? Like in time limit, like here the constraints are up to 2e5, right? So you can't really do n square. So how do you do it in time limit? So actually there is this structure called segment tree, right? If you don't know about segment tree, you have to read about it before watching this video. But what it can do is, like I'm talking about the lazy segment tree. Okay. So actually it supports two operations. One operation is that we can give it L, R, and value, and it will like set all the elements AI to that value. All the elements from L to R. L less than equal to I, less than equal to R. Okay. It will set all the elements to that value. Or you can uh, do a range query. Like this is called a range update. Okay. And you can also do a range query L to R. So it will give you the sum from AL to AR. AL plus 1 up to AR. Right. And it will perform both the operations in O of log n. So in O of log n, it can do both the operations. Okay. And like also it can find the maximum also. Like depending upon your join function, it can find the maximum from L to R as well. So AL plus 1 to AR, it can find the maximum, the minimum, like basically any function. Okay. So I can use this uh, segment tree to implement my logic. Okay. So initially what I'll do is, like, I have this array, right? I have the value array, value I, and I have the cost I. Okay. So for every index I, first I will compute, like let's say for this index I will compute that, um, if I change the cost, like basically for every index I will compute that till where can I go, till where can I go, so that I can use this cost. Like, see, in this test case, we saw that, let's say if I use this 8, like if I want to use this cost of 9, then I can go to these three files because they are less than equal to 8, right? So I can, like, I can update or I can delete these three indices using this 9 cost. So for this index, like for this index I can go from here to here. Okay. So for every index I'll compute initially that what is the range of its effect. Like if I make this 0 right here, make this 0 right here, then till where can I delete using the 0 cost? Like till what indices can I delete using 0 cost? Okay. And basically I can go to that index j, I can go till that index j such that the value of j is less than equal to value of I. Okay, so let's say I want to compute that how much right can I go from this index I, how much right can I go. So I can only go till the index where value of j should be less than equal to value of I, right? So let's say I have an array like this, 5 4 3 5 2 6 5 4. Okay, so if I'm here, if my I is here, then I can only go till this index, right? Because this 6 is greater than 5. So now again, how do I compute this efficiently? How do I find it efficiently? So for that, you can simply do a binary search. Okay, like simply do a binary search. Like let's say you check for this index mid. If this is your mid, your condition is that the maximum value from this I to mid should be 5. Okay, that's the condition. Or you can say that maximum value from I plus 1 to the mid should be less than equal to 5. Okay, so you can do binary search on the answer. Like on this right value, you can do a binary search, and like you can find out the maximum from L to R using segment tree only. Like in login time, you can find out, and login time would take for binary search. So that would be log square n. Or you can use sparse table. If you use a sparse table to find out the range maximum, it would be O of 1 into log n, like 1 for sparse table and log n for binary search. So you can simply calculate that for each index I. For each index I, you can calculate two arrays, pre of I and post of I. So pre of I means that um, how much left can I go, like till what index can I go, and post of I means how right can I go. And you can find this out using binary search and sparse table or segment tree, right? And then you want to do this, right? You want to do what? Basically, first you want to look at the minimum, right? You want to look at the minimum cost, which is 3. So you want to update, like let's say you have a new array here. You have a new array which stores the actual cost for each index. Okay. So for this 3, you will update these two indices to be 3. Because for this index I calculated that I can go until here to the left, and to the right I can go only till this index only. So this is the range for this element. So for this range, the answer is 3. Okay. Then For this three, I'll calculate the second smallest value. So for this index I, the range is still here. Okay, this is the range. So I will insert 3 and 3 here. Okay. Then the next smallest is the 6. For this index, the range is actually the entire array. So the entire array, that's the range. Okay. But here we already have a smaller value 3 and 3. So we won't fill that. We'll only fill 6, 6, 6. Right. But how do you ensure that? Because in the segment tree, this segment tree will actually update all the elements from L to R. Okay. Like I told you, L R val. It will set all the elements from L to R to the val. So how do you ensure that you don't override this 3? How do you do that? So my idea is that you can do it in reverse order. Like instead of starting from 3, just start from the highest value. Like what is the maximum value, maximum cost? It is 10, right? So start with 10. Okay. So like for this index, what is the range? The range is this. So 10 you will fill here. And for this index, the range is this. So 10 you will fill here. Okay. Then we have 9. So with this 9, you can fill these three indexes. So 9, 9, 9. Then you have 8 also. So using this 8, we can fill the entire thing. So you will replace the entire thing with 8. Okay. So 8, 8, 8, 8, 8. Right. And similarly, you can go from the top to the bottom. And at every blank, the last update would be the best one. Right. So you can simply do it in reverse. Like when you do it for 6, when you do it for 6, the entire thing would get updated. So 6, all sixes, right? And then when you come to 3, you would update these two to 3 and these two to also 3, right? So this is your final array. So this is what you can get using the segment tree, like just range set. Okay. And to find the answer, you can query for the sum. Like you can query for the sum from 0 to n minus 1, like for the entire array, minus the maximum from 0 to n minus 1. Okay. Now let's say you want to change some element to 0. Okay. Let's say you want to change this element to a 0. Then what you will do? Sorry, not this. I mean the cost. You want to change the cost to 0. So what you will do is for that index, you have calculated already that till where it goes, right? So you know that it goes until here, right? So you will just update all of these indexes to 0. That is the range update. Okay. And simply you can again perform a query of sum from 0 to minus 1 minus max of 0 to minus 1. So you can find the answer after this update. And let's say similarly you want to update this this 9 to a 0. Okay. So this index is from here to here. Okay. So it will change all of these three indexes to 0. So now the sum is something 6 plus 6 plus 6 plus 3, it is 24. I mean, sorry, 18. And minus maximum is 6, so answer is 12. So you can simply do this using segment tree. Okay. So that's how powerful our segment tree is. It can do range query and range update. Okay. So it makes this E very easy. So I hope it's clear. Uh, any doubts if you have, you can ask. I'll show the code. So this is for segment tree. Like it is a class. I just copied this code from somewhere. It has two functions: range sum and range add. Actually, range add, like this name is misleading. Like it was originally range add, but I changed it to range set. That is, uh, it sets every value from QL to QR to the this integer. Okay, and similarly, like this segment tree is for the sum, and this is for the max. Okay, and like in the code, I did what? I stored this vector of pair, right? And then I made this segment tree. And yeah, first of all, I found out all the post and pre ones, right? The post ones and the pre ones. That is, for every index, I found out that what is its range, right? So uh, for int I equals to n minus 2, I greater than equal to 0, I minus minus, like I found out using my linear search that what is post of I. So in this for loop, I am finding out post of I, right? So for post I, the low is equal to high, low is equal to I, and high equals to n minus 1. So while low is less than I, mid equals to this value by 2. And if the range max, like this L is a max segment tree, okay. So if the range max of this range I comma mid, if it is equal to v of I dot second, that is, if it is equal to the value at I, then my low equals to mid, otherwise high equals to mid minus 1. So this is binary search basic, and I find the, like how right can I go from I, and similarly I can find that how much left can I go from I. Okay, and finally, um, I have this vector of pair u. Okay, like I have basically the cost comma index. Okay, in this u, and I then sort it in reverse order. Like I reverse sort it. Okay, because I want to move from the largest to the smallest value, right? When I'm initializing it, I want to move from largest to smallest value. So I just reverse order it, and I have these two segment trees, one for the maximum and one for sum. And in both, like for index comma value in u, I just set that range to that value, to the cost, right? Like this is the cost comma index. So for that range of the index, I did the cost, and I do it in the reverse order of that thing, so as to make it correct. Okay. So initially answer is t dot range sum minus s dot range sum. So for s is the max inventory. So s dot range sum means s dot range max. Okay. And then I handle the queries int k c in k minus minus because zero indexing, and I will set the k thing to zero. Like I'll set whatever the influence of k is to zero in both segment trees, and again I'll print t dot range sum minus s dot range sum. Okay, and print new line. So this is the code. All right. So this was the code, and I hope you guys got it. Um, any doubts? If you have, you can ask right now. Okay, I guess you have no doubts. So I will end this PCD now. I'll take your leave. All right. So thanks for joining in, and bye everyone. Good night. I hope you all enjoyed it.